College Algebra, Chapter 3, Section 5, Graphing Techniques, Transformations. Objective 1. Graph functions using vertical and horizontal shifts. What are vertical and horizontal shifts? Well, they're taking a graph, not changing its shape, but picking it up and moving it up or down or right or left. Vertical being up or down, right or left is horizontal. So if we take, say, a function like the absolute value function, which of course, because you know all your common functions, is graphed, looks like that V stuff, right? Well, what happens when you take that same function and you add outside the function? Inside would be within these vertical bars. Suppose you add 2. Well, this does, outside the function works the way you suppose it should. Your V, so to speak, moves up 2. So outside the function works vertically and works the way you think it should. So if your function were the absolute value minus 2, then it would move down 2. You'd still have your V. Okay. What about inside the function, though? You can write this as the absolute value of x minus 2. Well, when you subtract inside the function, it's sort of the opposite. This looks like it should move to the left 2, because inside the function moves left or right, but it moves to the right 2. So inside the function moves the opposite of what you think it should. Instead of, when you subtract 2 moving to the left, it moves to the right, and you get your absolute value function. So if that function, f of x, is equal to the absolute value of x plus 2, because it's inside the function, we're going to move to the left 2. So just remember, inside, opposite. Adding and subtracting will be a movement left or right, up or down, but doesn't change the shape of your function. That works with any function, not just absolute value, but any of our common functions. What is objective 2? Well, let's see. Objective 1 was adding or subtracting. What happens when we multiply? And we can talk about division, but we'll multiply by a fraction in our division stuff. So this is graph functions using compressions and stretches. Compressions and stretches. So now the shape of the graph changes, but it doesn't move right or left or up or down, and that's where we used all those reference points for each of our common functions. So think of that reference point as moving up or down, left or right, but not moving when we compress or stretch. So let's see. Let's go back to our function, our friend absolute value of x. And remember, it is the V. Now, what happens when we multiply on the outside? On the outside works vertically. And on the outside works the way you think it should. So when you multiply by 2, you are doubling things, and it makes it a little skinnier. So if this point is 0, 0, the reference point doesn't move. But the 1 point becomes 1, 2. The negative 1, 1 becomes the negative 1, 2. So it gets stretched when you multiply by 2, which makes sense, vertically. If you multiply by 1/2, say f of x is equal to 1/2 the absolute value of x, 1/2 being outside the function, it still works vertically, but it's not a stretch, it's a compression. So 0, 0, the reference point doesn't move. But instead of 1, 1, it is 1, 1/2. Instead of negative 1, 1, it is negative 1, 1/2. It gets compressed vertically. It's like somebody putting their hand on the top and pushing down on the top. So this is a stretch outside the function vertically, right? This is a compression outside the function, so it's vertically. Inside the function, once again, things worked opposite. What is f of x equal to the absolute value of 2x? Now, sometimes a compression is a stretch, so to speak. So this works inside the function. It works opposite. So multiplying by 2 inside is sort of like multiplying by 1/2 outside, if that makes sense. So you are going to get a compression horizontally. Did I say that right before? It's not like multiplying by 1/2. If you're pushing on the top, that's a compression. Pushing down, that flattens this thing out. If you're pulling, you're stretching, and so this is a stretch. But a compression horizontally, pushing to the sides, you might think of both hands, right and left hands, pushing on the sides. It still looks like a compression. But it still looks like a stretch, but it is a compression horizontally, which makes it a stretch vertically. Does that make sense? So if we put in, say, a 1, we multiply this by 2, and then get that same stretch here. Does that make sense? But it's inside the function. This is also because the absolute value of 2x is the same as the absolute value of 2 times the absolute value of x. And the absolute value of 2 is always 2. Let's do another one. We're going to show you a different function so that it'll look, I guess, a little different also. Inside the function, f of x, absolute value of 1/2 x. Now, this would be outside the function a compression vertically, but inside the function it's a stretch horizontally. So a stretch horizontally means that instead of 1, 1, you stretch it horizontally and it's 1, 1/2. And a negative 1, 1/2. The reference point doesn't move. Now this doesn't always work this way. It does this because of this particular function and how the absolute value works, but it still is the same idea. This is a horizontal stretch even though it's a 1/2. This is a horizontal compression even though it's a 2, and it's because it's inside the function. Let's look at something that might make a little more sense as far as a stretch and moving inside the function. If we have the function, the step function, this function normally, and we'll just look at a few steps, goes from 0 up to 1, and then steps up to 2, and let's do 1 back here. Step, okay. So let's suppose we have f of x is equal to 2 times the greatest integer of x. This is outside the function. It works vertically. It is a stretch, so instead of this would still stay, that first step doesn't really move, because when you stretch it vertically, you're stretching from this x-axis. But it does move up 2 to get to the next step instead of the 1. That's the vertical stretch. It does move down 2 to get to that step instead of the 1. So that's the vertical stretch. Instead of 1 as a step, it's 2 as a step. If you do 1/2, it would be 1/2 as a step. So now, if this is 1, it just goes up. I'm sorry, first of all, the bottom step doesn't move. It goes up to 1/2 and down to a negative 1/2. What happens inside the function? That's where it becomes a little more obvious. The greatest integer of 2x. Now remember, this works the opposite. Even though a 2 looks like it should stretch it horizontally, it's a horizontal compression. So this step, which used to be from 0 to 1, it's a horizontal compression, goes 0 to 1/2. The step up is the same, because it hasn't changed the vertical stuff, just the horizontal. So now, hopefully you can see, stepping down, it only goes 1/2. I'm sorry, it only goes 1/2 left, but this is at -1. It's supposed to be at -1. This is a positive 1. It's the whole step, but only half of the width, because it's a horizontal compression. Let's see if I can do this next one right. 1/2 would be a horizontal stretch. So now instead of a width of 1, the width is 2. So our step from 0, but now it goes to 2. It still goes up 1 unit, but the width of the step now is stretched to 2. It still goes down 1 step, but now the width is stretched to 2. So 1/2 would be a horizontal stretch inside the function. 2 would be a horizontal compression inside the function. Remember, this step looks a little bad here. Does this make sense? Outside the function, it stretches it with the 2 and compresses it with a 1/2. Inside, compresses with a 2, stretches it with a 1/2. Vertical, horizontal. So if we tried to do objective 3, which is graph functions using reflections about the x and y axis, outside the function works vertically. So, and I just moved my screen again. Outside the function would make it flip over, because vertically it would flip. Inside the function would make it flip horizontally, just spin around, this side would be that side, and that side would be this side. So it would look exactly the same. Let's look at another situation. Suppose we have the square root of x. That is our function. Call it g of x instead of f all the time. What does g of x look like if it is the opposite of the square root of x? That's outside the function. It works vertically. So instead of above the x-axis, it will flip through the x-axis and below the x-axis. It would flip vertically. G of x equal to the square root of a negative x would flip horizontally. Instead of opening, in a sense, to the right, it would be up and to the left. Still be up, but that would mean this would have flipped through the y-axis. It is a horizontal flip. So that's the reflections you would get. In fact, that's problem number 28. Let's go through that. We're taking our function f of x equals the square root of x. They want to reflect it about the x-axis. Shift right 3 units. Shift down 2 units. And then write those out. Okay. So I reflect about the y-axis or x-axis. Well, remember, about the x-axis, instead of it being up here, it would be down here. So it is a vertical flip. So the negative has to be on the outside, negative square root of x, which is really a negative f of x. The second thing, shift right 3 units. Well, let's see, we want our graph to, instead of the reference point being 1, it will be over at 3. And then it'll do this. But if we shift right 3 units, we got to be inside the function because it's horizontal. And it's got to be the opposite of what we think. So f of x has got to be that square root inside the function x and 3, but we're going to subtract it to move to the right. Does that make sense? This is really f of x minus 3. I guess this x is a little bit, that's sort of lying in a sense. The original function is f of x. This is f of x minus 3. So, they want to shift down 2 units. Well, let's see. If we shift down 2 units, instead of it being here, it'll be down here. Well, that's a vertical shift. We need to take our square root and move it down 2. So, this is really f of x minus 2, right? The function minus 2. If f of x is the square root of x. Does that make sense? If we wanted to shift it up 2 units, it would be f of x plus 2. If we want to reflect through the y-axis, it would be over here, but that would be our square root of x. If If we're doing it horizontally, put the negative inside. If we wanted to shift left 3 units, that's that square root of 3. I'm sorry, square root of x plus 3. And that would put it here. Oops, it would be to the right though, because we didn't do it. If we wanted, we could put a negative inside, and we could do all of these. Let's do everything all together. How would we graph this function? I want 1 minus 2 square root of x plus 3. Well, let's see. What does this do? This takes our function, square root of x, moves it to the left 3, flips it, because it's on the outside, over the x-axis, stretches it vertically, and moves it up 1. Because this is really a plus 1 out here, right? So let's see if we can do that. So it's going to move it left 3. Let's take our reference point. That's why we call this a reference point. It's going to go left 3 and up 1. So that's going to be the new reference point. That's where that has moved. The negative means instead of going up and to the right, it'll go down to the right, vertically flipped. And the 2 is going to be a stretch, so it's going to be stretched further from this sort of new axis here. Left 3, up 1, flipped, stretched. Does that make sense? See if you can do these problems in section 3.5. We'll see you next section.